Okay, so let's move to lecture 1, introduction. Um, First of all, we are going to talk about the difference between thermodynamics and kinetics. In thermodynamics, um, people always talk about the equilibrium state. Thermodynamics define the equilibrium state. So always we talk about the equilibrium state in thermodynamics. So we I would say the states defined by thermodynamics or the equilibrium state defined by thermodynamics, this state can be considered as a reference coordinate. But however, the kinetics not the reference coordinate. Kinetics is depending on the path you choose. So we care about which path you choose from based on your starting and ending point, which path you choose, and it will have a corresponding velocity to get from start point to the end point. This is what we call a kinetics. And based on the kinetics, because it's like a moving, right? The atoms moves along inside your materials, the current passing through your materials. So it can be considered, it's not the equilibrium state. It definitely is moving. So in most of cases, in kinetics, we more care about the steady state. Steady state means that we have a steady flow process, J as a flux steady flow process and you using J flux to means that we have something passing through your materials. So here I can give you an example here. The thermodynamics give you a reference coordinate, right? So you can consider as like I live in Taipei, and now Tsinghua University is in Hsinchu. So Taipei and Hsinchu, um, this place can be considered as a reference coordinate. And how to traveling from Taipei to Hsinchu is the path you choose. You can choose take the high-speed rail train, or you can drive, or you can take the train. So the different paths you choose, then different time you spend from right. So this you can consider. So the thermodynamics give you some reference coordinate, and the kinetics, the most important part for kinetics will be you need to choose the starting and ending point. As long as you uh, define the starting and ending point by thermodynamics, then you can choose which path uh, you are interested in, and that will have a corresponding velocity. So this is an example. So then the third section we will talk more about in kinetics we more take care about the flow process. So how to quantitatively analyze or calculate or estimate this flow process is the most important thing in the third section. So we are going to show you, we are going to use the entropy production rate per volume sigma dot to quantitatively describe how slow or how fast this flow process is. So that will be the um, and also show you the beautiful equation to link the driving force to drive this kinetics process and uh, the flux, because we have a driving force to lead the flux, right? And this will drive the flow process, and all this and also this flow process will generate entropy. So we are going to prove this beautiful equation is the temperature times the entropy production rate per volume will be equals to the flux times the or dot the corresponding driving force. And in the last section, we are going to talk about if there are two or more driving force coexist into resistance, how to modify or how to deal with them. So we have the coupling of forces and flux, which means that there will be some interactions between two driving forces. Then we will talk more in lecture 4. So let's move to the first section. What's the difference between thermodynamics and kinetics? So I will start from my question would be how to describe a material system. Um, Probably the first thing come out from your mind would be when I describe a material system, I will use some parameters, for example, like the pressure, the temperature, the composition, and so on. So yes, the thermodynamic state is a function in a multi-dimensional space, which means that usually we always use the thermodynamic, some parameters defined in thermodynamic state to describe our material systems. That included like N1, N2, N3, N4 can be the composition, temperature, phase, pressure, and so on. So let's actually the F is a thermodynamic state. Actually, different parameters. We always use multi-dimensional different parameters to describe uh, a material system, and which usually would be which usually is defined by thermodynamic state. For example, like this on your right-handed side here, we have a lead tin phase diagram. And the vertical axis is temperature, and the horizontal axis is the composition, and it's a binary phase diagram. So we have a lead 100% lead here and 100% tin here. So any point, any point, any point inside this phase diagram is under equilibrium condition and also defined by thermodynamics. So for example, like this point at 183 degrees C and specific composition, and also also we have the liquid alpha beta phases. This spatial point or state actually we call is a leucitic point, and this point actually have a specific composition and also the specific temperature. This is how we describe these material systems. But if we slightly increase the temperature to 200 degrees C, would be the state will be here, right? The material system will be here, or the state will be here, and this will be at this specific conditions, the phase will be liquid. So we can use the composition, temperature, or also the phase to describe these material systems. And also, this will be defined by thermodynamics. And besides this, like parameters, this parameter, some people also use the energy state function to describe these material systems and also the process. For example, like the U is internal energy, H is enthalpy, Han, and A means the Helmholtz free energy, and G is a Gibbs free energy. You also can use the energy state function to describe the material systems. In addition to this, like different parameters, parameters, these state functions as well. So we can use, give you a quick summary here. We can use the, we usually use some state function to describe material systems. And this state function can be included this and also can be your energy. So when we learn, this is a quick review. Thermodynamics always talk about the equilibrium conditions only. So any states 任何一个状态，在热力学里面讲的任何一个物体的状态，讨论的永远都是平衡的状态 （equilibrium conditions only）. So I'm giving you an example here. So now we have like 6 states. F1, F2, F3, F4, F5, and F6. For the state 1, I call it F1, actually is under P1, under pressure 1, temperature 1, and also N1 is have a moles of something. So this is state, so we have 6 different states, and each state define, each state is equilibrium condition and also defined by thermodynamics. Okay, so you can predict the state. This state can also is this state actually means the state function of a material system under thermodynamic equilibrium, which means that this state function does not change with time. So the pressure is not going to change with time, temperature as well. So this state function, this state this state actually is equilibrium condition. So all the parameters does not change with time. This is quite important. So this is defined by thermodynamics. But if I choose state 1 as a starting point and state 6 as an ended point, then if I want to move my systems from state 1 to state 6, and I'm going to choose from state 1 to state 3, then move to state 6. This is the path I can choose. But probably you will say, Professor, how about choose the other path? Yes, you also can move from state 1 to state 4, then also go to state 6. So we have the same starting and ended point, but different path. We have the pink path and also the green path. So what's the kinetics? As long as you choose the starting and ended point defined by thermodynamics, kinetics actually is care about which path you choose. Is a pink one or green one, and also the corresponding rate or how much time it spent while you choose the pink path or you choose the green path. So this is kinetics care about. So there are 3 standard protocol or steps to deal with kinetics. The first one is you need to define the state, the starting and ending state you are interested in based on thermodynamics, equilibrium conditions. As long as you do that, then you decided which path you are going to choose. Then you can calculate or estimate the rate, the corresponding rate for a specific path you choose. So this is the whole story about and also the relationship between the thermodynamics and kinetics. So I'm going to give you a more close examples here. It's an ideal gas law. As you remember or as you're familiar with, is pressure times the volume equals to moles of gas RT, PV equals to nRT is an ideal gas law. What happens if I adjust or tune the pressure? What happens next? If I readjust the pressure or volume, that usually will lead the change in moles or the temperature, because R is a constant. So this is also give us some ideas. What ideas? Because I want to show you, if there's some change in mass and temperature, does that means we have the mass flux and also the temperature that would lead difference in temperature? So which means that probably that would lead the heat flux because we have temperature difference. So I draw a map from here. So also we also have the state 1 and also state 6 defined by thermodynamics. They are under equilibrium conditions. And also I chose the one for move state 1 to 4, then move to finally back to 6. So based on here, we find that during this process, doing this as long as because I already chose the starting point 1 and ending point 6. So this path, during this this path, we found the mass transport and also the heat flow. So this is also give you some hint or give you some idea about the kinetics. When we talk about kinetics, it always come with the mass transport, heat transport, probably the current transport. Okay, so I'm going to give you a summary about the thermodynamics. Thermodynamics give you a baseline for describing the state of a material system under equilibrium condition. Somehow it gives you a baseline to show you how to describe a state of material system. And you can use some parameters, and also you can use some energy functions to describe or define the state of your interesting material systems. And when a system reach equilibrium conditions, there are two criteria or there must two criteria need to be satisfied. The first one is no spatial variation in chemical potential, which means that no spatial variation in chemical potential, which means that atoms have same chemical potential. So no spatial variation. So when I try to draw a figure, it will be shown like this. The vertical axis means the chemical potential. The horizontal axis means the location. So all atoms show in these materials have the same chemical potential mu. So no spatial variation in chemical potential, which also means that no net mass transport. Yes, the atoms still jump to right-handed side, jump to left-handed side. But if I have one atom jump to right-handed side, there's must have the other atom jump to left-handed side. No net mass transport. And the second criteria will be total free energy is minimized, which satisfy the thermodynamics rule, which means that the energy of the system always is minimized. So any move and how to prove the total energy is minimized? The other in the other words can be say that any movement will raise the free energy of the system. So don't forget in thermodynamics, the total system always prefer to be minimized anytime, in any time and any conditions. So this is a summary for thermodynamics. Don't forget, like thermodynamics give you a baseline thermodynamics give you an idea how to describe the state of the material system. And also you can describe them by the different conditions, different parameters, and also energy functions. And don't forget the uh, when systems reach equilibrium conditions, um, we don't have any spatial variation in chemical potential, and also the total energy is minimized. So this is all this description is belongs to thermodynamics. So next, I try to give you an example to link the thermodynamics and also kinetics, and also the relationship between them. Okay, so let's consider chemical reactions here. And some people probably will call this a chemical reaction, or can also be considered as a phase transformation process. So now we have a constant or fixed temperature and pressure. And left-handed side, I have A moles of A and B moles of B. And on your right-handed side, you have some C moles of C and D moles of D. How to determine the reaction directions? How to determine that based on your background or based on your knowledge? How to determine this reaction is to go to right-handed side or go to left-handed side? How to determine the reaction directions? Probably some of you already have some idea, like energy dominate. We need to determine which energy, which state energy is minimized. Then probably that would be the older system will go that way, right? Yes. So let's try to draw the figure. The vertical axis means the free energy. Here, constant T and P, so we can use the Gibbs free energy as our indicator. And horizontal axis is the reaction coordinate. So we sum the free energy of our A and B, we got this high. And we sum our free energy of C and D, then we got this high. And obviously, you can find that we have a lower energy of C and D. So the system will go to right-hand side, will go this way, right? So thermodynamics give you an idea, can help you to determine the reaction directions. The delta G much smaller than zero, which means that the system always go to minimize the total system energy always prefer to go to minimize. So use this small value to minus this one, you will get negative. So delta G must be negative is we call a thermodynamics favorable. So whole system will go to right-handed side, and this is thermodynamics tell you. But thermodynamics did not tell you how long or how much time it takes to convert it to C and D, which means that the reactant A and B can totally generate C and D. Thermodynamics did not tell you this, but kinetics did. So kinetics will tell you how much time it takes based on how fast or how slow it will be depending on this activation energy. Delta E ACT. ACT means activation energy. If we have the small, or some people also call it as energy barrier. So if the activation energy is small, then it will be kinetics favorable. Okay? So this is the relationship between thermodynamics and kinetics. Thermodynamics can help you to determine the reaction directions, but kinetics can tell you how fast or how slow this reaction is. Next, as you know, as long as we have the kinetic, it means that we have a flow process. So before I move forward, I need to introduce as long as you have flux, which means that some driving force to drive this flux. So the flux, usually we use the J to represent the flux. And also the unit for flux, this flux is the entities can be numbers or energy passing through the unit area in specific period of time. So we call it as a flux. So in our lectures, there are three flux. You always, you need to know. The first one is we call a heat flux. So we use a J as a flux, and heat we will use a capital Q to represent the heat flux. And mass flux, we use the J and use the I or atom A, B, depending on, usually this is if you see I also means the atoms. And if you see the A means the A atoms or B atoms, or if a copper, we will use a Cu to represent the mass flux, the copper flux. And charge flux, in your textbook, they use the small q to represent the charge flux. So for the heat flux, actually you learn some laws regarding to the heat flux, which is quite famous. We call the Fourier's law. Is a heat flux equals to minus thermal conductivity. This is kappa times the temperature gradient. This is how we get or measure the thermal conductivity, right? You can measure the heat flux and divide it by temperature gradient. And the mass flux, actually, you also learn the famous fixed first law is the atomic flux equals to minus diffusivity times the concentration gradient, and also equals to negative mobility of the atom, concentration of the atom, and also the chemical potential gradient. This is a fixed first law. And regarding to the charge flux, which means like current passing through your materials, the most famous one we will call as the Ohm's law. It is the JQ, current density, and this is the I is the current divided by area, so we call it current density. Okay, so this is a current density, and Ohm's law actually more famous one would be a negative, and though is the electrical conductivity times the electrical potential gradient. And also negative electrical potential gradient can be is equals to the electrical field. So you can replace this as a low E. And in our textbook, because we use the sigma dot to represent the entropy production rate per volume. Sigma dot is where, okay. We use the sigma dot to represent the entropy production rate per volume. So regarding to the electrical conductivity, some people probably will familiar with the sigma, but because we use the sigma to represent the entropy production rate per volume. So here in your textbook, they use low to represent the electrical conductivity, low. Okay, so don't mess up the low and sigma here. So so here you can have some idea. If we have a temperature serving as a temperature gradient, that probably will lead the heat flux. If you have a chemical potential gradient, which means that atoms have different chemical potential that will lead atomic flux. If you have the electrical potential gradient, which means that the voltage drop or something like that, or electrical field that will lead the current passing through your materials. So for the kinetic, something passing through, which means the flux, we have some flux passing through your materials, that definitely exist some driving force to drive this flux. Okay, so don't forget that a flux equals to its driving force times the transport coefficient. So for example, like the heat flux and temperature gradient to drive it, and how to describe this, how fast or how small this material is. We use the thermal conductivity, and it's a transport heat transport coefficient. And some idea you can here who drive the atomic flux is a chemical potential gradient to drive it. And we also have the transport coefficient here is a mobility or diffusivity to describe how fast or how small the atoms moves inside this material, these solid materials. And for the current, the driving force is the electrical potential gradient, and the transport coefficient to describe how fast or how slow the electrons moves. Actually, we use the electrical conductivity of this material, so it is can be considered as a transport coefficient. Okay, so this is just for your reference. So back to uh, the kinetics. What is kinetics? Kinetics actually, because you have already have some idea about the driving force to drive this flux, and now we have a kinetics process, right? So kinetics, some people also uh, describe it as or define it as a rate of state function evolution. Evolution means that how fast or how slow it is. So the rate change of state function, the state function change rate, and state function also can be a free energy or entropy. So that may involve the changes of shape, size, composition, and crystal structure of materials. So the rate of state function change or evolution is the kinetics. And when under what kind of condition you can visualize this kinetics process? Some people probably will have some list like um, questions because professor, as you mentioned, we use the equilibrium condition to define the starting and end point. This is equilibrium condition. This is also equilibrium condition. How the state can change or moves from 1 to 6, because this is equilibrium, right? This is also equilibrium. Are there any external driving force to drive it? Otherwise, they both are equilibrium condition. There's no way this system is moved from state 1 to 6, right? And I will say you are right. So kinetics always only happen. The kinetics process happens from deviation of equilibrium state to equilibrium state, which means that there's definitely an external driving force to push the state deviated from equilibrium state. Then it moves to the other equilibrium state, and the corresponding path and rate is the process. This process we call the kinetics process. So, but my next question would be, yes, we already defined the kinetics process. It's deviated equilibrium state moves to equilibrium state. But how can we quantitatively describe how fast or how slow this kinetics process is? Are there any equation we can use? Otherwise, if there's no any equation we can use, how can we quantitatively estimate? So I would say we are going to use this thermodynamics rule you derive in thermodynamics to estimate the kinetics process. But how can we use these equations, these energy state functions derived in thermodynamics into kinetics? How can we do that? Because kinetics is something like a moving process, right? How can we use equilibrium condition, the rules defined, the equation defined by thermodynamics, directly use it into kinetics? So we make a very important assumptions to help us to quantitatively describe the kinetics, which we call we always assume local thermodynamic equilibrium in this kinetics process at any specific time and point. That allow us can make a like estimation or assumption make that can help us to make a estimation how fast or how slow this kinetics process is。所以在这里的话，主要是如大家知道了，在动力学的话，它是一个 steady state 的 flow process，所以我们如果要估算这个动力学的过程中，它这个动力学的 process 到底是快或慢的话，我们要估算它就需要一些 equation。那当然有一种选择是你可以新发展出、新推论出一个 equation，一个能量或 state function 的 evolution 来描述它。但在课本这里的建议是说，何不我们做一个，因为我们既然只是要估算它，那我们何不直接用热力学的这些能量 state function 的之间的这个 relationship 来直接拿热力学推导出来的 equation 来描述估算动力学的过程呢？那如果你要做这个估算的动作，你要直接拿从热力学推导出来的 equation 的话，那你就必须要做一些很严谨的一些假设，否则这样就不太 work 嘛。所以他这边就有假设到说，我们假设我们现在讨论的所有的动力学的过程，它都是每一个点、每一个时间点，它都是每一个特定的位置，然后特定的时间点，它都是 local thermodynamic equilibrium，所以就会让你可以直接使用这些 equation。因为我们有做这个假设，但这个假设的，so what this local thermodynamic equilibrium means？所以local thermodynamic equilibrium which means that in micro scale. So I can give you and it's assumed, right? So it's assumption. So I can give you an example. So probably we can turn to page like 17. I give you an example here. We have a metal bar here, and I have the heat reservoir on your left-handed side and and also cold reservoir on your right-handed side. And I assume the heat flow Q in equals to Q out, which means that we have a constant heat flux passing through these metal materials. So when you try to plot the temperature profile of this metal bar, you can get this profile. On your left-handed side, we have higher temperature, and on your right-handed side, which close to the cold reservoir, is you have a lower temperature. And due to Q in, the heat uh, flow inside this metal bar equals to the heat flow outside this metal bar. So this metal bar can consider as a heat transporter, right? So what's a local uh, thermodynamic equilibrium means? Which means that if you focus on this specific location, and we measure or we monitor the temperature at any because this is steady state, right? So which means that this temperature profile does not change with time. So if I focus on this location, the state function, which means that temperature here does not also change with time, but it's different with this point, this location. But at this specific location, local equilibrium, thermodynamic equilibrium happens because the state function does not change with time. The state function here means the temperature. If I look at this specific location also, the temperature T state function also does not change with time, but it is different with other locations. The temperature is different with other locations, but if you just monitor this local region, the state function does not change with time. So we call this as a local thermodynamic equilibrium assumed. So based on this case, each location can be considered as local thermodynamic equilibrium condition. So that will allow this flow process, this kinetics process, can use the state function derived, the energy state function derived from thermodynamics, can use this to estimate or to simply calculate this kinetics process. So this we call local thermodynamic equilibrium conditions. So next, how to describe this, which parameters will affect how fast or how slow this kinetics process is? Well, depending on two very important parameters. The first one, we will call it as a driving force. Driving force is the driving force just give you a quick reminder. Driving force, for example, if you are interested in heat flux, the driving force will be the temperature gradient. Okay, so the driving force will affect the rate of state function change. And the most important is the driving force is not only the magnitude, and the time period of acting or apply on the system is also important. Some people sometimes will forget the time period. And the second parameter is quite important, and is we call the inertia or mobility of the systems. So inertia 就是惯性, and mobility, actually, what's a mobility is when you apply the 1 unit of driving force, how fast or how slow your atoms moves or the electrons moves, we call the mobility of the system. So these two parameters, the driving force and also inertia or mobility of the system, will determine how fast or how slow this kinetics process is, which also equals to the rate of state function change. So I'm going to give you an example here. Is if we have we call a trunk versus the sports car. What this means? You can imagine that we have the same engine systems. I install it into the trunk and also the sports car. That use the same engine with the same horsepower. So which one can run faster? No doubt that will be the sports car. Why? Even though they have use the same type of engine systems, which means that the driving force are the same, but however, the trunk is heavy than the sports car. So that will lead the sports car can run faster than the trunk. So the inertia or mobility of system in this case, will dominate this kinetics process. So this is just an example to show you you cannot just you need to remember not only the driving force but also the inertia or mobility of a system. Both this parameter will dominate or can control the rate of state function change, can control how fast or how slow the kinetics process is. Okay, so let's move to and following. I'm going to give you like 3 examples, and I hope you can like based on the example I give to you. I hope you can find out what is the driving force and also what is the inertia or mobility of the systems in this in different specific case. The first one is the melting process. The melting process, which means that for example, like I have the melting something like I have ice cubes, and when you try to heat this up, then the ice cube will melting into water. So the phase will change from solid to liquid. So what happened inside here is the latent heat absorbed and the structure will renderize. So whole system, the entropy increase during this melting process. So I'm curious about, do you have any idea in this melting process? which is the driving force and which is the inertia or mobility of the system. Have any idea here? So the driving force here is the chemical potential difference or gradient serving as a driving force, which means that the liquid, the we have a higher chemical potential in liquid phase compared to in solid phase. So the driving force actually is a chemical potential gradient. But what's the inertia or mobility of the resistance? Ice cube. So I would say the thermal conductivity, diffusivity, or intermobility of this ice cube would be the inertia or mobility of the system. So you can imagine that if I added some sugar into this ice cube or added some salt into this ice cube, the thermal conductivity, diffusivity, H2O diffusivity, and interface mobility definitely would be different. So this is like, so you can imagine that the inertia or mobility of a system is more like a material property dominate. 在这个融化的过程中，事实上 driving force 是化学位能，也就是说，在液态的时候，它的化学位能事实上是比较低的，所以系统倾向走到能量比较低的，所以它就会融化。那在所以那 inertia of or mobility of system 比较像是这个材料的一些特性。在这个 case 里面的话，我要融的快慢的话，事实上跟这个冰块的这个冰块它的热导度，然后水分子的 diffusivity 跟 interface mobility 是有很大的关系。那大家可以想一下，如果我在这个冰块里面加了一些不同的成分，像我刚刚讲的加了糖或者是加盐，那它的这个冰块它的 thermal conductivity，它的这些 transport 的这些 kappa d 都会不一样。所以 inertia 或 mobility of a system 比较像是材料本质的特性。所以在这给大家做 reference，大家可以思考一下这个问题。那 the second example here is the creep. What's a creep? A creep actually is the atomic diffusion under a stress field to minimize the system free energy. Creep is like the chemical potential usually is high in compressive region and will be low in tensile region. So for example, like so that will lead the the driving force to allow the atoms move from the compressive region to tensile region. So I'm giving you an example to describe when the creep happen. So simply we can just hang a weight on the mat. You have a metal bar, right? You hang a weight under a metal bar. And as time increase, the metal bar will get longer and longer. Because when you hang a weight, that will lead a stress field acting on this metal bar, right? And as time increase, because you have a stress gradient, so that will lead the atoms move from compressive region to tensile region to minimize system energy. So that will lead this like metal bar get longer and longer. So this is we call a creep. So also the driving force will be the weight to cause lead the stress gradient, right? So what's the inertia or mobility of a system? You can imagine that even I handle same weight on like different metals, for example, like aluminum and silver, the total length will be same. No, right? That will depending on what? The mass transport, right? So the inertia of the system in this case would be the atomic transport coefficient, which is diffusivity. Diffusivity actually is just to describe how the atom moves, how fast or how slow atoms moves inside these materials. So if the metal bar we're talking about is a silver and the other is copper, I believe the diffusivity for copper and silver will be different. So even hand I hand on the same weight under both this metal bar, the total length will be as time increase, the total length will be different. That depending on the diffusivity of the copper, oh sorry, the silver and the copper. And the other will be the last case here I'm going to introduce to you or give you an example will be the grain growth. Grain growth actually is what's a grain growth? Grain growth actually is the diffusion mediated redistribution of the grain size, which means that grain growth means that we have the polycrystalline materials. We have a different grain, right? And the grain gets bigger and bigger, and the total numbers of grain decrease, right? But the average grain size increase, which means the grain growth. And this phenomena actually also minimizes system free energy. So always go this way. The grain always grows. So my question would be, what's the driving force for grain growth? Also, the chemical potential gradient. Why? Because for if you have polycrystalline materials, you have grain and grain boundary. For the energy potential, chemical potential energy for grain boundary is much higher than grain. So if you have more grain boundary, which means that total system energy is higher, so system tend to minimize the composition of grain boundary. If you can imagine, if I want to decrease the portion of grain boundary, which means that the grain, the the grain will grow, right? And the grain boundary gets smaller and smaller. So, so that's that's why I say the driving force is a chemical potential gradient. Because grain growth, we have more grain and less grain boundary with higher energy. So the total system energy will minimize. And which parameter or what is the inertia or mobility of um, this grain growth process would be the diffusivity of the grain boundary. If you have different composition of grain boundary, different materials, I believe the grain growth rate will be different. So this is the idea, even though you give them the same, even their chemical potential gradient will be the similar, but final parameter or the factor to determine the grain growth rate is also the diffusivity of grain boundary.